Hello. So what I'd like to do now is I'd like to talk a little bit about this technique that we're going to use to find things like the center of mass in the moment of inertia. But we'll look at it first in finding the volume and the mass. And then later on in the course, we'll look at things that are a little more complicated, just a smidge more complicated. But right now, I'd just like to look at the basic technique that we're going to use to do an integration of a solid object, right? So we want to be able to do something like figure out the volume of a cone, right? And the way we're going to do that is by looking at its area, right? So we're going to look at having little slices of this cone. So I can take this here, turn it into a slice, and we'll take these slices. This will allow us to turn this volume integral, this triple integral, into a single integral just by looking at the size of this cut that we're making in this cone. So we're making these horizontal cuts that are parallel to the base of the cone, and then we're going to find the area of each one of those cuts. Now the mass of that little disc there, right, is going to be proportional to that cut. So we can find through our scaling arguments this area. And so this area starts at something large, pi r squared at the base, and it goes down to something small, 0 at the very tip. So you just take the integral of this function, basically, to find the volume, because all we're doing is adding things up. So let's look at the reason why that works, right? So here's our cone, and we want to find the volume of this cone, right? So one thing we could do is we could estimate the volume of the cone by estimating the limits for this thing. So what could we do? We could say, well, one limit is that we have a cylinder, right, that goes over this entire cone, right? So we could come over here and just draw a cylinder like that. Find the area of this cylinder, and that would be a limit. But we'd know that this cylinder is too large for this cone, right? We see that there's all sorts of empty space outside of the cone but inside of the cylinder. So this cylinder that has a volume of pi r squared h, right, the area of the base times the height of the cylinder, that's way too much, right? We don't need all of that. So what could we do? Well, we could cut it up into smaller cylinders, right? So we could take like 5 cylinders and start with the base here, right? Start from the base and go up a fifth, in this case, of the way. And then say, okay, take another cylinder that is at the edge where the cone meets the cylinder there, and pile on another one. So that's reducing in size. So we have this 4/5 r squared, right? So that's 16/25 times r squared. And that is going to be the radius of the base of this second of the cone after you've cut off the bottom here, the bottom 1/5. And we keep doing that. So we have one that's 3/5. So we have one that's 2/5. And finally, we have one that's 1/5. And that covers the entire cone. And that gives us a volume of 11/25 r squared h, right? So this thing here is also too large. And you can see that just like when we used just 1, that was too large. Now when we use 5, it's way up here. When we use 16 of these little cylinders, it's dropped way down here. So it's gone from about 4.5, right, to that may be 4, to 0.36, right? So it's dropped a lot, 0.45 to 0.36. Then we go to 100 of these things. If we put 100 of them together, it would be about 0.34, let's say, something like that. So it gets smaller and smaller and smaller and smaller and smaller. Right, so that's very good. That's sort of what we want. The more of these cylinders we get, the closer it comes to the cone that we are stacking the cylinders on top of. We could also stack the cylinders on the inside, right? So we've shifted these down, so now we've got these orange ones. The outline is the yellow outline is the old cylinders here, right? Or the old stack of cylinders, the 5 cylinders there. 5 cylinders on the outside, we have 4 cylinders on the inside, and you can see we've got the cone interior in between. So this is going to be something smaller, and as we get closer and closer, as we add more and more of those cylinders, these two numbers get closer and closer together, and they're going to be around 0.32 to 0.34, somewhere in that range. You can kind of guess what the answer is going to be, but it's going to be somewhere in between for this 5, 1/5 of the volume of the cylinder that contains everything, right? Just the cylinder of the same height and base of the cone, and 11/25 of the same object, right? So it's somewhere in between these two numbers. 1/5 and 11/25 is going to be the volume. So that's what we want to find now, is the exact number for that volume. You can see what this looks like, right? You can see, this is 1 over the number of cylinders. We're going to an infinite number of cylinders. We get to an infinite number of cylinders, it's going to be some number. These are converging on some number. They're getting smaller and smaller and smaller. So the heights of these are getting smaller as we have more and more of these cylinders. So as n goes to infinity, what we're really doing is we are ending up doing this infinite sum, or what we remember as an integral in calculus, right? So that's this integral, right? We saw it a little bit before. What we're going to do is we're going to integrate from the base, 0, to the height of the cylinder, h, and we'll use the area here, this area of this slice, right? And dz is going to be the height of this infinitesimal slice. So this dz is really infinitesimally thin, right? It's somewhere between 0 height and the first rational number, whatever that would be, because it really isn't a first rational number. But, it's something in there. It's infinitesimal. It's smaller than the smallest possible rational number, 1 over whatever the largest natural number would be if there was a largest natural number. But there isn't. So, but there are an infinite number of points in between 0 and that 1 over the largest number that actually doesn't exist. So that dz is what we're going to integrate by. So this thing in here, an area times a height, right? The area of this circle times the height of the cylinder, which is infinitesimally large, is basically a volume of one of these extremely tiny cylinders. That they're so tiny that they're two-dimensional, right? So they're actually circles. So we're going to add up these areas with the integral this time, rather than with multiplication, or like we did with the cylinder itself. The one large cylinder was just a multiplication, or the number of cylinders where we added up things together. So this is just an extension of what we were doing. This is doing the same thing over and over and over again until we got to something really strong. Okay, so something that we can use mathematically. If we wanted to find the mass, then, well, we have to multiply by the mass density. But if we were going to do that, we end up with is this linear mass density, lambda z. This is one of these things that you can get even if you don't have this change of shape, right? We're going to create this lambda z using these arguments that we were just talking about with all of these cylinders, right? We're going to say, well, this lambda at some height z, is going to be the area, 1 over the of this circle times rho. So this is a dimensional analysis problem. So we can think about this in dimensional analysis terms. That's part of the reason why it's in this part of the course. This is helping us solve a problem here, right? We're saying, okay, we've got this infinitesimal slice of this cone. What is the mass density of that slice? Because it doesn't have a real mass, because to get a real mass, you have to multiply by this dz. That dz has to be a finite number to make it a true mass. So it's not a real mass until we do the integral, is what really happens. So that's where we're going, right? So to find this lambda z, we multiply az times rho, right? The area of this circle times the mass density, and we can go on. Now, there are other ways we could construct linear mass density. We can look at the density at the top, the density at the bottom, and draw a line, right? Or it doesn't have to be a straight line. Your homework, you do have a homework problem like this, your homework asks you basically to draw that straight line for lambda z, which is the same function basically as this, only it doesn't have a zero. We're going to have a zero at the top, because a of z is 0 right here, right? So at the very tip of our cone, we get no contribution to the mass, and we get a maximal contribution at the bottom. But we have to find this function of the area as a function of z, and that's going to be a scaling argument. That's going to be a dimensional argument, right? So the first thing we have to do is figure out, so we want to find the mass of the cone, and we just said we wanted to find the mass through an integral that included the area of the circle. So we need to find the area of not just this circle, but every single circle along this height, right? So that starts down here at the base, and it ends up here at the tip. So we need to find the area of each one of these circles, and we find that by finding the radii of each one of these circles. Okay, that's not too hard, right? Because we already know what it is at the top, we know what it is at the bottom, so we just have to write that lambda z that we showed earlier, that function, that straight line function that goes from the area at the bottom, which is pi big R squared, to the area at the top, or which is 0, as you increase the height. The z here is the height, right? So this is all it is, right? We have r at the bottom minus z, right? We're going up here times the slope, right? This thing is reducing in size. So how much does it reduce in size per z you go up, right? Well, that's the scaling part, right? We're sort of scaling this radius, and it reduces, right, such that when we get to the top here at the height h, r minus z times r over h is equal to 0. Well, what would that be? That would be z is equal to, well, that requires the r over h, right? That's where that comes from. So we've just thought a little bit about it, and we can write that particular thing. We just match the conditions that we know. Very straightforward. Possibly I should look at that. So that's the answer. So let's see what we're doing. So what we want to say here is that we want to find the slope here, z, so it's z times m now, so that at r of h, at the top, this is equal to 0. Okay, so this is the function we're solving for, right? So we know that r of 0 is the radius of this entire thing. So that's where the big R comes from, right? That's what we started talking about at the very beginning. The base of this thing has a radius R, so that's what we start with. And we also said at the tip we have a radius 0, we have an area 0. So we want to find this m, right, at z equals h. So we can change this z here to an h, right? So now we have r minus h times m is equal to 0. So then m is going to be equal to r over h with our basic sort of math, right? So I think we've gone over that enough right there. That gives us this r over h. That's where each one of these pieces comes from. And then I have to turn that into a large R. Then I just pull out the big R, and then I end up with a nice simple function here that I can use later on. So the area of the circle, what happens with the area of the circle? The area of the circle, we just square the little r squared, right? And when we do that, we end up with our big R, pi r squared here, times this factor, right, the 1 minus z over h squared, right? Because that's the factor that's reducing. So this function is of z is basically a quadratic function, right? It's right up there, right? It's just a polynomial, right? We just have a polynomial, that's all. And that's what we're going to do the integral on, right? So remember, we had m is equal to az times rho, okay? And we wanted to integrate that. That is going to be rho times the entire volume. So you can see, right, if I just pull the rho out, we have the integral here, 0 to h az times dz. That's just the volume of the cone at times rho. So rho is not changing. The density of the material is not changing in this problem. It can change. One of your homework problems has it changing. In that case, the shape of the object isn't changing. That's actually a cylinder. So this lambda doesn't have to change that. It doesn't have to come from a change of shape. But we do the same thing, right? We construct our integral. And in this case, this is a quadratic, right? So that's what we're going to do. We have the pi r squared rho times this integral over this unitless function, and that's going to give us something that will give us the actual volume. So the first thing we do, we have this quadratic in here. We actually boil it out, square it out. 1 times 1 minus 2z z over h plus z squared over h squared. Yeah, just what I wrote down there. So perfectly normal thing, something you're very used to, right? So we just FOIL it out. Now we have 3 functions that we have to integrate, right? So we've got just 1, so that's going to be z. The integral of 1 is z. Integral of from 0 to h of 1 dz is equal to h. Then we have this one here, which is 2z over h. The integral of z is 1/2 z squared, and then we're going to have to insert that h in for z at the end. So that's going to be 2 times 1/2 h squared over h. That's going to be h again. And then, well, and you see that these two terms here, when we do the integral, these two terms cancel out. And just this, the integral of this quadratic term, which turns into a cubic term, 1/3 h cubed over h squared ends up just being 1/3 h. So 1/3 h is basically what we have, 1/3 pi rho r squared h. So that's the example. That's how you go through it. It's fairly straightforward. Not a lot of trickiness here. All we're doing is we're using all of this knowledge that we've built up over such a long time in school. What is the shape of something, and so forth and so on, to construct this integral. right? And this is what we do in physics, is we actually construct the integrals. That's what we want to do, is we want to figure out how to do these things by thinking about them, right? What are we doing here? And this is the technique here that lets you use all this geometry knowledge to make something that might be a little tricky into something that's not tricky at all. So this is what we ended up with, right? So we wanted to find the mass by using this volume, right? And when we did that, we just multiplied rho times this a of z. We see that these two partial sums, or these, they're not partial sums, these sums of these cones, these covering cylinders for the cone, converge. So the covering at the top here, over here it had 11/25ths, but it kept on reducing towards something around 0.34 or less. And then we had these orange cones on the inside of the cylinder, or cylinders on the orange cylinders on the inside of the cone. Those increased, going towards 0.32 or greater, and our actual integration gave us 1/3 r squared h right in between them, right there, and that was our actual volume of the cylinder. So the idea here isn't what is the volume of the cylinder, it's how to find volumes, or not the volume of the cone, it's the volume, it's not to find the volume of the cone. The idea here is, of course, how do we reason about these things, right? How do we use some of our ideas here? And we had to use some ideas about scaling, right? We had to say this, where is it? This radius of this circle has to change, right? So how do we figure out how it's changing, right? Well, we know the shape here. Now, I could give you a really weird shape, and this would still work, right? And I can draw any shape I want with an infinite polynomial and ask you to do that. No, I'm not going to, but you should be able to construct an area of something like that. In this case, it's fairly simple because we just need to figure out how the radius scales as we move the circle up, the cut up the cone, right? So that's just sort of what proportion of the way up the cone have we gone, right? The same thing would be true if we had a square cross section, right? If we had a square cross section, we could also do something like that. So I think that's all we really need to talk about there. That's all you need to do something like this, to find this 1/3 r squared h. Very simple, very straightforward. Okay. So thank you very much, and I will see you in class. Bye now.